All right, so the problem of the day yesterday was looking at radical halogenation. And I wanted you guys to do the stepwise mechanism for the halogenation part and then show me what the product would be after reacting it with a strong base and acidic conditions. So let's go through the mechanism first, and then we'll put the product down. The very first step in radical mechanisms is always going to be initiation. So we've got bromine and UV light. So we've got Br. And when we react this with UV light, we're going to get two bromine radicals, right? And so let's show the homolytic cleavage here. We have to remember to use our fishhook arrows showing each electron traveling separately to each bromine. And now for the second step, we need to do propagation. So for propagation, we've got a few different things going on. In the first step, we need to do a halogen abstraction. So we use one of these bromine radicals to grab a proton in this position. And then the other electron gets dumped down onto the neighboring carbon. And we get a tertiary radical along with Hbr. Why don't I take a proton from anywhere else?
That's the most stable.
Yeah.
It's the most stable radical. I know I have a tert-butyl group on the end, but there are no protons on there. There are 3 methyl groups, so even though it appears to be more substituted, you can't abstract a hydrogen from there. All right, so the second step of the propagation is the halogen abstraction. So we use this radical that we formed in order to react with bromine. So in this case, we're going to have one of these electrons meet up with the covalent bond between the 2 bromine atoms, and then the other electron go over to the other bromine. So we get that along with our bromine radical. All right, so this is our product of interest. And then last but not least, we need to kill off our radicals. There are 3 different ways we can do this. I'm just going to show one. We can just have coupling of our 2 bromine radicals in order to reform our bromine that can subsequently be reused in the reaction. But with these reactions, they're always composed of 3 steps. The first step, you make your radicals. Second step, you do all the reactions with your radicals. And in your last step, you have to terminate or dispose of your radicals somehow.
So that is to say that if we were doing this, we would break it down exactly like this?
Yes, there's always an initiation, propagation, and then termination step.
I have a question. I kind of asked you earlier.
Yep.
But for this one, you make the radical version, and in the second step, you use one of them. How come in the third step you can't use the other one? Why do you have to use a brand new?
So in this case, when you're reacting bromine with UV light, only a small portion of that bromine is turning into radicals. So you have a lot more of that Br2 around than you do of bromine radicals. So it outcompetes.
I understand that, but I still don't understand why you can't just use the other one that you already made.
That's what I said.
You could use that as your final termination step, and a lot of people do. But you'll see when we get to radical polymerization that this is the overall scheme for most radical mechanisms, is the initiation, propagation, and then termination.
Okay.
You can do that, it just makes the radical polymerization look a little different. Yeah?
For this step, the last steps, is there going to be examples where the problems where there's not going to be just half the atom?
So you can have your halogens couple, you can have your alkyl radicals couple, or you can have your halogen radical and your alkyl radical couple. You can show either one of those. It really doesn't matter to me. All right, so we've got this top portion figured out. Now in this next step, we're reacting it with sodium hydride, which will favor an elimination reaction. And then we're doing acid catalyzed hydration. And will that favor the addition of an alcohol in the Markovnikov or anti-Markovnikov position? Markovnikov. And so now we're able to turn an alkane all the way into an alcohol. And this was something I wanted to show you guys, is that normally people use radical halogenation in order to make a useful intermediate that they use for further synthesis. So this is a really valuable synthetic tool that we have. We can convert it to alkenes, we can do substitution, we can do reactions on the alkenes that we make. There's a lot of different options here that we can go with. So this is an example of how we can go straight from an alkane to an alcohol. Are there any questions with the problem of the day?
This kind of stuff will be on the test tomorrow.
Yes, this kind of stuff could be on the test. Anything new from today will not be on the test.
Okay, great, thanks.
Yep.
Next time. It is.
I couldn't tell if that was sarcastic or not.
I'm being serious, but that's the last.
I'm being sarcastic.
No, I'm not.
All right, so the next section from chapter 11 that we're going to cover is allylic bromination. And this looks very similar to what we've covered before. So let's take a look at
Yes, we should review.
this group. Where are the allylic positions on cyclohexene?
Very top and very bottom.
Very top and very bottom. Those are going to be the most reactive positions on here, and why is that? What's special about the radical if we pluck a hydrogen from either the top carbon or the bottom carbon?
Resonance stabilized.
It's a resonance stabilized radical, right? So we mentioned yesterday that these allylic positions are particularly susceptible to radical halogenation. So if we go through this mechanism, or actually just through the reaction, we're going to skip the mechanism for right now and say, all right, let's react this with Br2 and HV. We know that those are the most reactive positions. So naturally we would say we'll get some sort of bromine added to the most reactive position, right?
Well, I didn't both sides of this one.
So what happens if it reacts on the bottom instead? It's the same molecule, right? So we're not overly concerned with whether or not it attacks the top or the bottom. If we add an excess bromine, it could add to both potentially. But let's assume we have one equivalent of bromine. Does anybody see a potential pitfall with using bromine in this reaction? Think of chapter 9.
Yeah, it can pop off.
What happens if not all of it's being turned into radicals and we have elemental bromine around?
We'll continue to do it.
Oh, we have further bromination.
It can do a bromination across the alkene, right? So from chapter 9, we saw we can get anti-bromination across an alkene. So a side reaction is, let's assume we've got Br2 that's not been initiated, it's not a radical yet. If we do that, then we get this side reaction. Plus the enantiomer of that. So,
When the bromine finds that 3-membered ring, yeah.
yep, you go through a bromonium ion intermediate. So the problem with this is that you get a side reaction that is very difficult to control. The question is, how can we get around this side reaction? We only want the radical. We don't want elemental bromine. We don't need plain Br2. We need Br dot, or the Br radical. And there's a special reagent that's been developed that does get around this problem. So the alternate reagent and this alternate reagent has a 5-membered ring with a nitrogen in it. And it's a cyclic amide with a bromine coming off the nitrogen. And so if we take this reagent and we react it with UV light, the bond between the bromine and nitrogen will be cleaved, and one electron will go over to the bromine, the other electron will go over to the nitrogen, and now all we get is our bromine radical. we don't end up with any elemental bromine that's Br2. And the name of this reagent is called N-bromosuccinimide.
That was a fun one.
Succin.
So we do this, that way it can't affect the double bond.
Exactly. This will not react with the double bond because we only have a radical. A radical can do addition reactions to double bonds, but in this case, the allylic position is the most reactive position here. Instead of people saying N-bromosuccinimide, people just say NBS because it's a mouthful. And so we can use NBS in order to install bromines into the allylic position within molecules. So let's take an example of this using our previous reagent. If we take cyclohexene and we react this with NBS and UV light, we only get bromination at the allylic position. We get no side reactions that we saw with using elemental bromine. So now we've got a really useful tool in order to start manipulating allylic positions on fairly complicated molecules. So let's take a couple more practice examples of this because I think it makes more sense when you see it through examples. So let's look at a more complicated example. And this time we'll kind of break it down into pieces a little bit more. So we've got NBS and we've got our UV. So let's go through and actually do the mechanism for this. So what will the first step be? Will it be initiation, termination, propagation? Initiation. So first step will be forming our bromine radical.
Oh, that's our NBS, right?
Yep. So I'm going to draw out our skeleton and then fill in the arrows next. So we're doing a homolytic cleavage here. So we've got our initiation going. We've created a very reactive radical. Now the second step is we have to do hydrogen abstraction. Whoops. And we said that the allylic hydrogen is very, very reactive, right? So we've got Br, and we know the allylic position will be over here, so we can think of a proton being right there, and we've got this Br dot. These can couple together, and then the other electron will get dumped here. Plus HBr. So very similar mechanism to radical halogenation. But what's the problem with this radical? Or I guess not problem, benefit of this radical?
It's stable.
Resonance stabilized, right? So let's draw the resonance form of this. If we do this, this electron can come over, that electron can come over, and then the other pi electron can go onto that terminal end of the alkene. So now we've got a resonance delocalized radical. All right, so now the next step will be reacting it with our bromide radical, or Br dot. And so if we think about it, we've got two different positions that this can add into. Let me think of a good way to draw this. I'll do it this way. I'm going to have an arrow going down here and an arrow going down here. I know this isn't the best.
Plan poorly.
But we know that this bromine can add into this radicals position, or it can add into this terminal position. I know this makes our notes kind of complicated looking.
Especially when you have one pencil.
Yeah. Oh, that's your one. Isn't that color?
All right, so for the top one, we've got our bromine added in to the original allylic position. And in this case, we do have to pay attention to enantiomers, right? Because we know that we are forming a stereocenter. So we get this plus an enantiomer. And along with that, we get a new product where our bromine is now coming off of the terminal position. So with allylic brominations, you can oftentimes get two products because the radical that we form can be resonance stabilized and it can reside on either of those carbons, and either of those carbons can react with a bromide radical in order to form our new halogen species.
Are both considered major, or is one worse?
Both are considered
Because that's
to be potential products. If you look at the resonance form on the top, it's the more stable radical, so those are going to be your major products. The one with the bromine coming off of the end will be your minor product. So that's a good point. Let's label that out. So major products and minor products. So or minor product, yeah. So you always have to look at your radical, assess which one's going to be the major resonance contributor, and that will be the one that is most reactive. The last step will be your termination. So we've got Br dot, and I'm just going to have it react with Br dot. And this can give Br2. But at this point, we're more or less done with the reaction. Ideally, you don't want to make very much Br2 because that can react with your alkene. But I'm just trying to show your termination step.
I thought it was fast. Wouldn't that GR2?
Yeah, oftentimes these reactions can be a little difficult to control, but in this case, you're not probably going to generate much. So there are other termination options available. Oh. Shoot. In fact, the mechanism I showed up here is technically a termination step because we're ending up with no radical species. In this case, you don't really need to show your termination step. All right, does that make sense with the allylic halogenation? It's very similar. The one thing that tricks people is that the alkyl radical that you form in the intermediate step is resonance delocalized, so oftentimes you can get multiple products out of it. All right, so let's take a step back and think about a reaction we studied in Chapter 9 where we skipped the mechanism. We talked about halogenation, specifically anti-Markovnikov halogenation, and we said that it proceeded through a radical mechanism. So radical addition of Hbr. And so we've already seen this in Chapter 9, and we said that if you have an alkene plus Hbr, you'll get bromination at the less substituted side, or sorry, the more substituted side. And so we call this a Markovnikov addition. And we said when they were originally studying this reaction, they noticed if they used impure reagents or anything with peroxides, that it would be anti-Markovnikov. So I'm just going to abbreviate this ROOR. And if you do this, you get anti-Markovnikov addition. And I alluded to the fact that this mechanism involved radicals and we weren't going to cover it at the time, but now we actually get to go back and see how this mechanism works. So the overall mechanism is very similar to the mechanisms we've already talked about. What's our first step going to be? Initiation, right? So in this case, we've got a peroxide. That oxygen-oxygen bond in peroxides is particularly weak and susceptible to homolytic cleavage. So our peroxide is going to act as the initiator. So we've got ROOR. And when we do this, we get two radicals out. And it's through a homolytic cleavage. So one electron gets dumped to each oxygen. And you can do this a few different ways. The covalent bond between oxygen is so weak that typically all you need is heat. You don't need to apply UV light. So we'll just put the delta symbol under there. And then the next step is, now that we have a radical, and this is in the presence of Hbr, we can do another step where this oxygen's electron will be donated. The covalent bond will be donated to form a new bond to that hydrogen, so it's a hydrogen abstraction. And then bromine gets an electron. When we do this, our peroxide now becomes just a plain old alcohol. And we've created a very, very reactive bromine radical. Now that we have our bromine radical, we can do some propagation. So this was initiation. Now we'll do propagation. So let's take a look at the example that we have up here. We've got Br dot. So we've got a radical and we've got a pi bond. Yesterday we saw that radicals can react with pi bonds, or they can react with allylic positions. In this case, it's going to react with the pi bond itself. And so what we get is a new bond there, and then the remaining electron in that pi bond gets dumped down to that adjacent carbon. So the question I have for you guys is, why don't we get the other product that looks like this, where the bromine adds to the more substituted side and we get the radical over there? So why is the bromine adding to the terminal end of that alkene rather than the more substituted end? Yeah, the radical is more stable. So if we look at our radical stability here, the one on the left is a tertiary radical, the one on the right is a primary radical. So in this case, the one on the left is much more stable. So in this case, the primary radical is not observed. All right, now that we've got this radical, we need to add on our last proton. So we've got one more step. I'm going to jump down to the next line. So this tertiary radical that we've formed can react with hydrobromic acid that's in solution, and it can do a hydrogen abstraction. And then the bromine gets an electron. And now we've got a hydrogen up here and our bromine right there, along with our Br dot. What's our very last step now that we've made our product of interest? Termination. So if we have Br dot and we've got Br dot, these will combine together to form Br2. And so this is the reasoning behind why peroxides cause the bromination to occur at anti-Markovnikov positions, is because the intermediate, we want to go through the most stable radical, which occurs on that primary or tertiary position. Yep.
So for the termination
second row for the second number,
Mhm.
whatever, can we just put the BR live instead of having the HBR like you did in the
You can do that. That is one of the termination options. But the reality is there's a lot of HBr in solution, so that's going to outcompete the bromide radical that's in solution. If you drew it either way, I'd be fine. This is the way that is more accepted by polymer chemists in particular.
Would the bromine from the HBr ever add in to where the radical is? So you'd have two bromines in the product? Or that's not possible?
That's a good question. It doesn't occur very readily because the hydrogen abstraction occurs so much quicker. I'm curious, though, if there is ever observation of a side product with some of that. I'll have to look into that. All right. So radical addition of HBr is really useful for getting anti-Markovnikov addition products. But when radical chemistry really starts to become interesting is with polymerization. So we're going to spend the rest of lecture talking about polymerization. These mechanisms are useful for synthesis, but I was reading somewhere that I think over 60% of all organic chemists work in the polymer industry now. So the next reaction I'm going to show you is what the bulk of organic chemistry is nowadays. So let's move on to radical polymerization. There was actually a research group at UW that just made a giant breakthrough in polymerization reactions, and I'll try to post that on the topic of the week next week so that you guys can see it. But essentially, they've devised a route that doesn't use any metal catalysts for their polymerization. So if you're looking at going into bioengineering, so maybe developing plastic pieces that go in between spines, you can't have any trace metals in that plastic or else you could poison your patient. This new research is actually finding ways around using metal catalysts, and they can use pure organic catalysts that are much, much cleaner reactions. But I'll post that next week for you guys to take a look at if you want. All right, so with radical polymerization, you always start out with some sort of alkene. And I'm just going to abbreviate this with R groups. And these R groups can be just about anything you want them to be. And polymerization just means you're going to link up a bunch of these together. We'll go over the mechanism here in a second, but with polymerization, what you get is you get a new carbon-carbon bond. And these will repeat over and over again, so oftentimes people will bracket them out. That just means you've got a repeating unit of a carbon chain, right? So this can be going on theoretically forever. The product on, or the reagent on the right is called a monomer. So mono meaning one, and the product on the right is just going to be called a polymer.
What does that little N thing mean?
So N is the number of repeat units. So this could be N equals 5. It could be N equals 100 million. We can try to stop polymerizations at certain steps in order to control the length of that polymer. And by doing so, they have entirely different properties. That's a good question. So the monomers we can choose greatly impact the properties of the resulting polymer. So let's go through and list some of the most common monomers. So one of the most common monomers is just ethylene. That's a carbon-carbon double bond. The next most common one probably is propylene. The next most common one after that is probably styrene. And it has a phenyl ring. I'm just going to abbreviate it PH. And then after that, we've got something called vinyl chloride. So a vinyl group is synonymous with an alkene, and this time it just has one chlorine coming off of it, so they call it vinyl chloride. That's actually allowed by the UPAC naming system. You could also call it 1-chloroethene if you wanted. It doesn't really matter. And then the last one that I think is pretty cool is tetrafluoroethylene. ThyLene. All right, so if we think about the polymer that we can make out of these, what do you think the polymer of ethylene is called? Polyethylene, right? So polyethylene, if you look at the bottom of your plastic soda bottles or water bottles, you can oftentimes see PE as an abbreviation. PE stands for polyethylene. Polyethylene is just a repeating unit of these carbon chains. So we've got hydrogens here and here. And these can repeat. And depending on the length of the polymer or the branching of the polymer, they can have entirely different properties. But these are very commonly used in commercial plastics. I'll just say plastic water bottles. How about that? It's pretty cool. We didn't have access to these polymers until about World War II, so these were pretty cutting edge when we were able to make containers that were reusable and lightweight, especially when we had a shortage of supplies during World War II. The next one is going to be polypropylene. Oops. Does anybody know what polypropylene is used in?
Heard it before.
Heard it before?
I swear I have.
It's used in plastic bottles.
It's also used in plastic bottles. So it's got a CH3 group replacing one of those hydrogens. The other really common use that's not as common anymore for polypropylene, but I still use it because I love it, is clothing. So a lot of camping gear is made of polypropylene. So if you've got long underwear, especially older, like, well, not old, but made a while ago, oftentimes they use polypropylene because it's an excellent insulator, as opposed to cotton. If you wear wet cotton, you're going to be very cold camping, but polypropylene, if it's wet, will still keep you warm. So polypropylene is used in clothing and carpet.
We talked about it in our hiking class.
Yep.
I swear.
So carpet is another big industry where you use polypropylene. Styrene can actually be made using a couple different polymerization methods, but one of them can be radical. So we replace one of these hydrogens with a phenyl group. You can actually get an acid catalyzed polymerization instead of radical polymerization. And polystyrene is really common in styrofoam. Oop. Oh, I'm not spelling styrofoam right. S-T-Y-R-O-F-O-A-M. So those styrofoam packing peanuts you get, or the styrofoam bricks you get, these are almost always made of polystyrene. Some of the newer ones are actually made from biodegradable materials. So a lot of companies are trying to get away from plastics and switching to things made from like potato starches. And so a lot of the plastic industry is trying to get away from polystyrene because it's hard to break down in the environment. It'll stay in landfills for a long time. All right, so the next one is vinyl chloride. If we polymerize that, we replace one of those hydrogens with a chlorine now.
Is that just polyvinyl chloride?
So it's polyvinyl chloride.
PVC pipe.
Exactly, I heard somebody say it. PVC pipe. So PVC pipe is used in a lot of homes. It's the easiest pipe to work with if you're an amateur plumber. It's a lot easier to work with than copper for a lot of people. So it's used in houses. So PVC, it's used in piping. Oh. So it's used in
also used in some Michael Kors bags.
It's used in what?
Michael Kors bag, it's a handbag. I work.
It's used in handbags too, apparently. That's a useful thing. All right. And then my last and arguably most favorite one is if we have tetrafluoroethylene, we're going to replace all of those hydrogens with fluorines. Does anybody know the name of this plastic?
Polytetrafluoroethylene.
Polytetrafluoroethylene? Yeah, that's kind of a mouthful, so there's a more common name.
Ptfe.
Urethane? Toothpaste.
So Ptfe is often used. There's a brand name. I'll give you a hint. Think of cooking. Teflon. So this is what we put on pans, oftentimes. The reason it's so great is it's very, very hard to break carbon-fluorine bonds. They're very strong. They can withstand high heat, and they don't react with the materials that you're cooking on a hot surface, so they're nice and non-stick. So it's a non-stick.
Almost have a cheese Teflon pan going to place.
I like this. This is chemistry that applies to real life.
I know, right?
Cooking with fluorine.
Yeah, so like I was saying, over 60% of practicing organic chemists work in the polymer industry. This is why. These are a lot of very, very useful commercial products that without having these, our society would be a lot more troublesome. All right, so let's take a look at how this reaction works because it's an interesting mechanism.
And Colin, do you have?
I'm going to switch to a new page here. So the first step is always going to be our initiation, right? So we can use a variety of different radical initiators, and oftentimes it depends on the industry that you're using, or at the industry that's producing it. I'm just going to choose a peroxide because we've already seen this before. And if we react a peroxide with heat, we can homolytically cleave the bond between the two oxygens, and we can get two radicals out. Now the next step is, let's say we've got our alkene, like our monomer that we showed on that first page, and we've got a radical. We can have addition to the pi bond. So if we do this, this can come over. One of the pi bond electrons can come over, form a new covalent bond, and then the other one gets dumped onto the end. And now we've got a highly reactive alkyl radical. Right? So we've done the full initiation step, and now the interesting part is the propagation. So with propagation, we take this alkyl radical, and it's assumed that you're running this in a big batch. In this case, I'm showing ethylene. So this can continue adding and do another addition to a pi bond. And now we've got RO. And we've added two more carbons onto our chain. And if you've got more ethylene in reaction, then you can just keep on going and say, all right, let's dump one more down. And then that will go over.
I want two more.
Yep, we just keep on adding carbons in groups of twos, and we can keep on doing this over and over and over again. And this is called the chain growth or propagation step in polymerization. So that's why we call it propagation. In our radical halogenation, it's not really a propagation, it's just additions and abstractions. But in polymerization, you're always growing a chain, so it's propagating the chain along. Now the termination step is also pretty simple, and there are two options. We can have I'm going to just abbreviate this. So let's say we've got some long chain polymer, and we've got a radical at the end. Occasionally this will find another radical. What was that?
But they'll become friends.
And they become friends. This radical hops over and couples with the other one, and you just get one long extended chain. Let's see if I can count carbons right. Is that right? So you end up connecting the two alkyl chains. I may be missing a carbon there. I'll fix it later, but you get the idea. You can terminate it by coupling two of your alkyl radicals together. That's one option.
When doing things like these and you have little pieces in the end,
Mhm.
does it even really matter how many if your carbons are added up?
Right.
Technically, there's
The big thing is they're going to be even number, right? Because we're always adding the carbons in pairs of twos.
so as long as it's an even number.
Yeah,
Okay.
as long as it's an even number. It can be anything from 2 all the way up to 1,000,000. The other option is if you've got this alkyl radical, you can have this find some of your initiator and it can terminate. This is actually a very active area of study. And oftentimes you can purposely add a radical in to be a capping group onto the end of these polymers, and you can try to functionalize them a bit more. So you've got a long polymer chain with a functionalized end group. And you can get some pretty unique and interesting polymers out of these reactions. So either of these methods for termination works well. The other interesting thing with these reactions is there's often a side reaction that occurs. So I'm going to break the page here with the line. So with our side reaction, we still go through the same intermediates. But you may have noticed that our alkyl radical here is on a primary carbon, right? I just got through telling you guys that primary radicals are very unstable. They don't like to be primary radicals, and so oftentimes they'll find ways to form a more stable radical. So you get this side reaction that can be fairly challenging to control. So let's say you've got this radical, and you've got some other long chain of carbons. I'm just going to abbreviate this N. And you've got 2 hydrogens there. What will happen is that this radical will come over and abstract a hydrogen from over here. And then the other electron will get dumped down onto that carbon. And when we do that, we start branching a polymer. So now we still have our normal chain. Along with our new terminated polymer. And this polymer over here can now do an addition reaction with the new alkene. Oop. Gotta get my arrow bigger. And then the other group adds on the end. And this can keep on going. All right, so we've taken a straight chain polymer and we've started branching it because In this case, in the top right-hand corner, we're forming a secondary radical that is much more stable than a primary radical. So this is a very significant side reaction for these polymerizations. So you can imagine this. All right, this can keep on going. Oop. It shouldn't be double-headed. I'll just do one more unit to emphasize the point. And it can keep on going, so I'll say etc.
And then can that do it again, where it takes the hydrogen and forms a brand new branch?
Yeah, oftentimes you get not only branching, but cross-linking of polymers too, right? So if you've got two long polymer chains, they can even cross-link together, right?
They form like a ring.
Kind of. It's more of a meshed network of polymers. So there's cross-linking and there's branching.
Can you like go in reverse for all this?
No, once you start forming a polymer, it's pretty hard to break it down, at least reliably. I mean, you can burn it and try to decompose it, but getting it to be reversible in a controlled fashion is very hard.
Plastic doesn't break down.
Yeah, plastic is very hard to break down. So cross-linking. And branching can be controlled to some extent via catalysis. And the really interesting thing with this is we realized that by controlling the branching and cross-linking, we can control the physical properties of the molecules. So typically, the more cross-linked and branched something is, the more rigid it becomes, the less flexible it becomes. So we have some plastics, like shopping bags, that are very flexible, and then we have other plastics that are nearly as hard as steel. And so by controlling the polymerization process, we can control the physical properties of the plastic. We control...
What plastic is like steel?
I saw one recently where they were trying to make essentially shatterproof glass, and it looked just like normal glass. It didn't look like the plastic glasses that are used today. It looked just like normal pane glass, and they could take a sledgehammer and drop it on a pane of it and it wouldn't break. So they're developing a lot of these hybrid plastics that they embed with some metals. And yeah, that's the big application is phones and computers. They're trying to develop things like Gorilla Glass that are incredibly strong polymers that don't break very easily.
When chemistry class in real life was so much more fun.
And I think that's where we're going to leave off today. Remember that we're going to be meeting in 302 at 6:15. You can email me or stop by my office if you have questions.